So here we have a cart that weighs 5 kilograms and it's attached by a rope through a pulley that's frictionless and weightless, so we can ignore it. And it's attached at the bottom of the attached rope is a hanging mass that's 4 kilograms. And we are given that the initial velocity is 0 and our coefficient of kinetic friction is 0.4. And we want to find the change in position, and so we have to say that there's acceleration, because this hanging mass is going to accelerate downwards and this cart is going to accelerate to the right. And in order to find the change in position, we have to find the acceleration. So let's do that. But first, let's draw our force diagrams. Okay, so for the cart, we're going to have weight downward and normal force upward, but because it's not moving or it's not accelerating or moving in the upward direction, these are just going to be equal. And we're going to have friction to the left and tension to the right. The tension vector is going to be longer because we know that the cart is accelerating to the right. It has to be, the net force has to be greater than the friction, so we'll know that it's accelerating to the right in the direction of its tension. And then for the hanging mass, we know that there's tension by the rope upward and its weight downward. And because it's accelerating downward, we know that the weight vector is going to be longer than the tension, or it's going to be bigger. The force, the weight is going to be bigger than the tension of the rope. And we just draw our vector sum diagram, and we'll know that the net force is going to be downward, so the acceleration is downward. And same for the cart, acceleration and net force are going to be in the same direction to the right. Okay, now we can find our friction using this equation, coefficient of friction, which relates to our surface, times our normal force. And so this is basically, I forgot to mention that the acceleration of the cart and the hanging mass are going to be equal because the tensions in the rope are going to be equal at both points. And so we calculate the friction. It's going to be 20 newtons. Oh, I forgot to mention the normal force. Excuse me. The normal force is going to be the same as the weight of our cart. And we know that the weight of our cart is 50 newtons because 5 kilograms times the force of gravity, 10 newtons over 1 kilogram, is going to equal 50 newtons. And so that's our normal force. And then we get our friction. Oh, I did that right there. Okay, now that we know that, I'll mention again that the tensions on both the cart and the hanging mass are equal. And we want to find our acceleration, so we're just going to try and find, or we're going to try and basically plug in numbers until we can isolate the acceleration in the equation. Okay, we'll see. The tension of the cart is equal to the net force plus the friction. You'll see that here. This is the tension vector, and the net force plus friction is equal to the tension. So we're just trying to define our tension in terms of what we know. And we know our mass, and we don't know our acceleration, but we know our friction. And for the hanging mass, we'll go up again. For hanging mass, we know our weight, it's going to be 40 newtons, and we know our, we know that we know our mass, and we don't know our acceleration again, but the acceleration of the hanging mass and the cart are going to be the same. So now we just have to equal them to each other. And we just isolate our acceleration, and then finally we can plug in numbers. and we'll end up with 2.2 meters per second as our acceleration. Now we can draw our acceleration time graph, and the area under the acceleration time graph is going to be our change in velocity. So we get 3.3 meters per second. So that means if our initial velocity was 0, then our final velocity was 3.3 meters per second. Okay, now we can draw our velocity versus time graph, because eventually we want to get our change in position, which is the area under the velocity versus time graph. And it comes out as a triangle, so we just use formula for our triangle, and we get 2.5 meters as our change in position, aka displacement. Our change in position is 2.5 meters. That means that in total the cart moved a total of 2.5 meters as it was going to hit the pulley as the hanging mass was being pulled downward. Let me see. Yeah, so as the hanging mass was pulled downward, it was accelerating, and the cart is going to move a distance of 2.5 meters before it hits the pulley. Well, it's going to change its position by 2.5 meters until it hits the pulley. And that will happen at 1.5 seconds, I think, if I remember Mr. Dade saying to us that the cart is going to crash into the pulley at 1.5 seconds. Yep. Okay. Thanks for watching.